Okay, so let's get started where we left off in the previous class. Okay, so in the previous class we were looking at fluid reactions. We will take gas liquid reactions as an example. The analysis that we are going to do with respect to gas liquid reactions, it's very much valid for liquid reactions also. What we are going to assume is the component A from the gas phase is going to dissolve in the liquid phase. Component B will be in the liquid phase, and A and B will then react in liquid phase. Okay. Again, it need not be gas phase versus liquid phase. You can very well extend this to phase 1 and phase 2. Phase 1 can be gas or liquid, phase 2 can be gas or liquid as well. Okay. So, that is what is going to happen. A from phase 1 is going to dissolve in phase 2, and then A dissolved in phase 1, A dissolved in phase 2 and B dissolved in phase 2 are going to react in phase 2. Okay. So, that is how we are going to do the analysis, and the examples of gas liquid reactors that you came up with are on the left hand side over here: bubble tower, trickle bed, spray tower, tray column, airlift reactor, and on the right a few reactions, SO3 reacting with water to give sulfuric acid, hydrogenation reactions, and CO2 capture in liquids such as monoethanolamine. Okay. So, these are some of the reactions that are of interest. Okay. So, let us also then talk very quickly about the various theories that people have looked at. So, there is two film theory, which is very similar to what we have been talking about in the last 3 weeks or last nearly 4 weeks now, and there will be a film on each of the fluids where all of the diffusional resistances we will assume to be present only in the film. Okay. If there is no reaction taking place in the film, as is the case in fluid 1, we will have the concentration falling or pressure falling more or less linearly. It will not of course fall linearly if the surfaces are curved. For straight surfaces it falls linearly. If surfaces are curved, del square equal to 0 and del square has the r square term or r term in it. Okay. So, for Cartesian coordinates you will get, or whatever for rectangular case or for flat interface you will get that to be constant. In phase 2, in this case we have taken phase 2 as liquid, in phase 2 you are basically going to have diffusion and reaction. Okay. So, that is what we have done so far. Okay. So, let us actually start off from here. Okay. And let us consider in about 2 weeks back we had used Excel to consider extremes of your Thiele modulus, right. So, when we took a Thiele modulus to be very, so this was our pellet. Okay. So, when the diffusion was very fast, okay, which means Thiele modulus was approximately equal to 0, what we got was the concentration CAS. Okay. When okay, or phi square was much less than 1. When phi square much greater than 1, what we had was fell to 0. Okay. So, this was for solids. Okay. So, but this is not necessarily related to solids. There was nothing really about the fact that this is a solid. It was only about the fact that this is species A that is undergoing reaction. When it comes to the two fluid example, species A is undergoing a reaction and species B is also undergoing a reaction, and therefore the situation is slightly different in so that is the only difference, but conceptually the idea remains the same. If the diffusion rate is significantly faster than reaction, your concentration of A that is diffusing remains more or less flat. Under extreme case, you can consider to be flat. Okay. In the other end of the spectrum, if the rate of reaction is extremely fast, your concentration of A is going to fall as soon as it encounters the other species. Module 5, as soon as it encounters the catalyst, the concentration falls to 0. Module 6, as soon as it encounters B, its concentration falls to 0. Okay. Now, when it came to shell and core model in module 6, what did we have? Okay. If there was internal diffusion resistance, this will fall over here, and thereafter it will fall to 0 if it is it's a very fast reaction, right? Why? Because here there is no reaction. Okay. So wherever A is not encountering B, okay, there is no change that is happening. Okay. As soon as A encounters B, it will immediately fall to 0. Okay. What if your phi is of the order of 1, phi square is of the order of 1, phi square is from 0.1 to 10, or phi is from 1 by 3 to 3. What do we observe in that case? We observe the case to be somewhere in between. Okay. So, in that case your concentration might fall like this, your concentration might fall like this, or your concentration might even fall to finally to 0. Okay. But it is going to be some kind of a CAB concentration that will be there. Okay. So, those are the limiting cases. I will erase this because I do not want to complicate things. Okay. So, the limiting cases okay. In gas liquid, again that is because of the history of how the gas liquid reactions evolved. This particular thing is called instantaneous reaction. Okay. Very slow reaction case will be one limiting case. The instantaneous reaction case for gas liquid will be the other limiting case, and then you have the cases that are intermediate between the two. Okay. And in gas liquid reactions, this historically through the work of various researchers, amongst which Doraiswamy and Sharma were lead researchers. Sharma again worked with Dankwards, and the surface renewal theory was from Dankwards group, and followed that legacy, and then they analyzed a whole bunch of gas liquid systems. Lot of it coming because of the industrial problems in the Bombay-Pune belt. So Sharma was in UDCT, and Doraiswamy was in NCL, and there was a lot of problems in organic and in mostly organic synthesis, but organic and inorganic synthesis in the Bombay-Pune belt, and that was the time in 1970s to 1990s where a lot of those problems they addressed, and a lot of those problems were in gas liquid systems. Okay, so that's where a bunch of this, and this is of course it's a global thing, but very much contributions from Indian chemical engineering community, and they categorized these various different types of limiting cases of reactions in 4 regimes. Okay. And again, if you look at some of the theoretical work talks about one unified approach where all of the regimes except the instantaneous regime are considered under one framework. The instantaneous regime is considered under a different framework, and I will come to that later on in today's lecture. Okay. Whereas because a lot of development in gas liquid reactions happened in collaboration with industries and in collaboration with medium scale industries also, not just large industries like Reliance and NoCell and so on, but also medium scale industries, and were involved in a lot of this development, and therefore to solve industrially relevant problems you needed to generate easy tools rather than always relying on simulations in order to get an answer. So what breaking down the problem into 4 different regimes allows us to do is have a textbook approach to 3 of the 4 regimes, and only one of those regimes you need to use a little bit more detailed approach. So that's been the history of gas liquid reactions, and I said that because Doraiswamy's book is one of the books that I have recommended for further reading on this. Okay. And if you are interested in NPTEL, there is an NPTEL lectures by Professor Sanjay Mahajani. The gas liquid systems that he does, he has a very nice analysis of gas liquid systems in case you are interested. Okay. So from Froment and Bischoff, this is the overall situation when it comes to our gas film and liquid film. Okay. Very similar to what I had shown over here. Your gas film, there is no reaction, there is only mass transfer, and therefore that particular mass transfer is going to be governed by, as we have always done, okay. And in this regime, diffusion plus reaction. Okay. Now, as I had said, we will assume that PAB and CAL are somehow measured or known. Okay. You do not have to solve for it, Okay, what that means is, let us say this is taking place in a column reactor if it is a flow reactor, or it is taking place in a batch reactor. We should be able to sample the liquid and we should be able to sample the gas and measure the concentration in the gas phase or the liquid phase. So, therefore, those values are measured or known. Okay. We will want to predict them, but those are known, but the concentration at the interface or the partial pressure at the interface is something that was not known. Okay. Why? Because it is extremely difficult to probe the actual interface. Okay. We now have techniques that allow us to probe the interface, but those techniques are extremely expensive and they are not, will take a lot of time in order to probe the interface. So, for example, if we are running the reaction in our lab, in order to probe, let us say the reaction is say CO2 plus amine. Okay. In order to probe what is happening over there, we will take a pipette, we will draw out a sample, we will take that sample and immediately quench it in a known amount of very cold liquid. Okay. Why cold? Because we want to stop, we want to arrest the reaction. So, the reaction stops as soon as it gets in touch with the cold fluid. Okay. Let us say we take 1 ml and dissolve it in 99 ml of liquid. That means whatever you measure from that liquid that you have gotten, you just multiply it by 100, that was the concentration originally, right. Now, you can measure the concentration of amine and you can measure the concentration of CO2, both of them. So, you will get the concentration of amine will give you CBB, B is amine, concentration of A will give you CAB, concentration of A in the bulk liquid phase. That is how we measure. Okay. Very similar to the experiments that you might have done in your undergraduate or in your 11th and 12th as well. Okay. Now, if you want to measure what is happening at the surface, that is extremely difficult. Okay. So, for example, we have a proposal that we have put in with respect to measuring on the surface, and in the reactor it is very difficult to measure on the surface. So, instead what we are going to do is we will take one single drop of liquid B, okay, and then we will pass on gas with gas A on top of it, and then we will use some kind of an IR type of a technique in order to measure the interface. And that also we are not going to be able to measure the interface only, we are going to be able to measure average over several thicknesses on the interface. Okay. So, those measurements are extremely difficult. On the other hand, the bulk measurements are fairly straightforward, and that is the reason why all throughout we will assume that your bulk concentrations are measured, your interfacial concentrations are not. Okay. Periodically we might measure interfacial concentration maybe once a year or so on if we get access to those equipments, and then we will use them to validate the models. But otherwise running of the models will be done based on the bulk concentrations only. Okay. So, that is the reason behind why this is developed in this particular manner. Okay. Now, reactions happen only in liquid or reactions happen only in phase 2, it is an assumption. Okay. It could have very well happened in phase 1 as well. Very few systems, extremely rare that the reactions will happen in both phases. Okay. Most of the time it is going to be the gas that dissolves in the liquid and the reaction takes place, or it will be A that dissolves in from liquid 1 to liquid 2, and we usually have a good idea of where the reaction will take place. Okay. Now, the films will exist in both phases, as we have talked about. Okay. And A in gas and A in liquid are at equilibrium. Okay. We can use Raoult's law or we can use Henry's law. Right. So, either of them, which one to use? Whatever is appropriate for that system needs to be used. For the most part, we will basically use Henry's law over here. Okay. So, let us talk about solubility of A. Any questions so far? Okay. So, this was just talking about the species in the gas phase, the species A that was present in the gas phase. Species B was present in liquid, okay, and the concentration of species B in the bulk liquid, we can say that is CBL, okay, and that will also drop because of reaction. Okay, and this particular value would be CBI, and we will assume that not enough B goes into the gas phase. Okay, that's just an assumption. That's usually, when it comes to non-volatile systems, that's usually what happens. We usually run experiments in cases where you want A to dissolve in the liquid, and therefore the pressure and temperature are such that B will not vaporize in the gas phase. Okay, so that's how most of these systems are run. Okay, so that's a reasonable case. Okay, again we will, for the most part, we will talk about A, but same thing we can talk about B as well. Okay, so let's now talk about A. The reason why we talk about A is because the picture of A is a little bit more complex, because there is diffusion, that is diffusion happening in the gas film, then there is dissolution happening, and then there is diffusion plus reaction happening in the liquid film. On the other hand, for B, only diffusion plus reaction is happening in the liquid film, there is nothing that is happening in the gas film. Okay, that is the only reason. You could switch A and B and the analysis will just be a little bit different, that is all it will be. Okay, one species is diffusing in phase 1, diffusing plus dissolving in phase 2, and diffusing plus reacting in phase 2. Another species is only diffusing and reacting in phase 2, there is nothing that species does in phase 1. Okay, and you can very well replace phase 1 and phase 2 and the analysis remains the same. Okay, so do not worry about that aspect. Okay, so Henry's law basically talks about the solubility. The Henry's constant H, okay, and in some cases Henry's constant H is defined as concentration in the liquid divided by partial pressure in the gas. In some cases is defined in terms of partial pressure in the gas divided by concentration in the liquid. So in this particular case, this H is defined in terms of CAI, that is moles per liter, divided by PAI. Okay, and just to ensure that we know what this is, I have put that in a different color. Okay, concentration of A dissolved in the liquid phase at the interface divided by partial pressure of A in the gas phase at the interface. Okay, so where maybe I will use one more color over here. Okay, so this is the situation, okay, and they are in equilibrium. Okay, so if this is the Henry's constant, this is partial pressure of CO2. Okay, can you calculate the concentration of CO2 in liquid? Yeah, straightforward. H multiplied by P. That's all. Okay, this is something that I had talked to you in the previous lecture, right, when we discussed this. If we have film theory, our K in the liquid phase, or well, sorry, K in either of the fluids, K is proportional to diffusivity by film theory. That is the theory we are using. K is proportional to the square root of diffusivity if for both surface renewal and penetration theories. Okay. Tau is kind of the residence time, the time that a packet spends before the surface gets renewed. Okay. On the other hand, and again, I mean, if you look at kind of dimensional analysis, right, this is in terms of meters per second, meter square per second divided by second, meter square per second square. Okay. Very bad way of doing analysis, because here this is meter square per second divided by meter, that also gives meters per second. Okay. Where does it come from? It comes from the assumptions behind the theory. Okay. One is the film theory. What is the assumption behind the theory? The molecule traverses a distance of delta. What's pushing it? The concentration difference. How much it is going to be pushed? Based on the diffusivity. Diffusivity determines how fast that particular set of molecules move. Okay. On the other hand, surface renewal theory talks about, let us say there is a packet that comes to the surface and it spends certain amount of time over there and then gets mixed or gets reacted. Okay. How does that come about? That is kind of, you can think of that particular small part of the surface like a semi batch reactor. Okay. And then if you do that analysis, you will get dA divided by tau. What does penetration theory, how does the penetration theory work? Not exactly right, but you can think of this as pi d divided by V is some kind of a time constant. Okay. The concept is very different with respect to penetration theory and the surface renewal theory, but you can think of that as the amount of time that packet spends on the surface. So, that is the equivalence between surface renewal theory and penetration theory. Again, when I say equivalence, I am just giving an example to explain. This is not how the theory works. Okay. If you were to match the two theories, this is how you think about it. But the theory, I mean, if you are interested in the theory or if you need to look at the theory, Doraiswamy and Uner's book would be a good place to start, or even from Enden Bischoff. Okay. So, that is the background. Do not have to bother about the background. We are going to talk about film theory. Film theory, Kc is proportional to diffusivity to the power 1. Okay. Right. Mass transfer in the gas phase, we have talked about this, Kga multiplied by Cab minus Cai, which is equal to Kpa multiplied by Pab minus Pai. Okay. What is the equivalence between Kg and Kp? It's C is nothing but P by RT, RT comes out. Okay. That is essentially what happens. Okay. And then these are the 4 regimes of operation: very slow reaction, instantaneous reaction, and then the other 2 cases of fast versus slow reaction. Okay. Now, why do those 4 regimes come in, whereas other authors tended to have looked at 2 regimes? Because you have A and B. Okay. A diffuses very fast, A diffuses very slow, A diffuses in between, B diffuses very fast, B diffuses very slow, B diffuses in between. Okay. First case is where A and B are both slow, last case is where A and B are both fast, compared to reaction rate always, right. The middle 2 cases are when A is fast, B is slow, and A is fast, B is fast. Okay. That is why those multiple regimes come about. Okay. Okay. So, we will pause over here for a minute, let you, so let us look at the cases. what happens when you have very slow reaction rate? Okay, very slow reaction rate, also known as very fast rate of diffusion. Both A and B rate of diffusion is much faster than the rate of reaction. As a result, the concentration of A does not change, concentration of B does not change. Okay. How is this value related to this value? Henry's, okay. PAI is related to CAI with Henry's law. Okay. Now, there might be case where there is no gas phase diffusion limitation or no liquid, there might be a gas phase diffusion limitation. That we are not talking about, we are only talking about what is happening in the liquid phase. Okay. Very likely if the reaction is so slow that the concentration is in liquid phase is flat, there is nearly no chance that there will be mass transfer limitation in the gas phase. Why? Diffusion rate in the gas phase is much higher than the diffusion rate in the liquid phase. Okay, that is the reason why. Exceptions might be there, extremely large gas and very small liquid droplet. Okay, so spray tower, very small liquid droplet, very atomized liquid droplets, that might happen. Again, quite unlikely that it would happen, but yeah, I mean, in rare cases that might be possible. Okay, yeah, but anyway, we have this PAI related to CAI using Henry's law. Okay, and the overall concentrations are going to be equal to the bulk concentration and the interfacial concentration. Okay. So, that is the case when you have extremely slow reaction rate. Okay. Now, when you have the reaction rate as instantaneous reaction rate, A and B do not see each other. Okay. There is no region where A and B are both simultaneously present. Okay. This is what we talked about in this particular situation, okay, where A falls to 0 as soon as it contacts B, B falls to 0 as soon as it contacts A. That the original authors called it as instantaneous. Okay. What is the difference between this and this? Over here you can see this region is a region where both A and B are present. Okay, A and B are present and they are reacting. Okay. On the other hand, if this particular situation was to become like this, if you are to zoom into this region, in this region your A would be falling like this and your B would be falling like this. Okay. Now, this particular region is negligibly small, okay, just like this region over here was negligibly small, and you could take your eta equal to 1 by phi approximately, right, like that is the situation. But we are not going to get into any complication like this, we are just going to ignore that particular possibility. What we are saying is wherever A is present in the liquid phase there is no B, wherever B is present in the liquid phase there is no A. Okay. What does that mean? That means, let us say this was, you can think of this as a reaction front. Okay. The reaction front is infinitesimally small, the thickness of the reaction front for all practical purposes is 0. What is the other thing that means? No reaction is taking place over here, there is only diffusion. Why? Because there is no B present. It is not like A and B do not want to react. Okay. In the very slow reaction case, A and B do not want to react or react very slowly, and therefore there is no change in the there is no reaction in the liquid film. Okay. In the other case, there is no reaction in this half and this half of the liquid film, because there is no A present in the right half, there is no B present in the left half. Okay. The reasons are different, but the idea is the same, that there is no reaction okay. So, these are the two cases which are typically easier to handle, and these are the two cases that take some amount of analysis. What equivalents you can draw to the solid phase system? The equivalence that we can draw to solid phase system is when the Thiele modulus, the square of the Thiele modulus lies between 10 and 1 by 10. Okay. So, that is the regime that we are talking about in this case. Okay. So, in one case your concentration of A is falling in the liquid, but concentration of B does not fall. In the other case, both concentration of A and B are falling in the liquid phase. Okay. So, those are the two situations that we are going we will handle. This situation becomes a little bit easier to handle. Why? Is because we only have to solve for A, we do not have to solve for B. This is going to be a little bit less easy to handle, because both A and B are falling and reaction is taking place. Okay. That is the only difference. So, in one case you have one ODE and CB in the liquid equal to CBB, that is this case. In this case there is reaction and diffusion for both A and B. What is the equation for reaction diffusion? 0 okay. And if the reaction is AA plus BB giving products, your RA is nothing but minus A multiplied by KCA to the power alpha, CB to the power beta. Your RB is nothing but minus B multiplied by that same term. Okay. So, these would be the equations. Okay. For regime 2 we are assuming CBB is constant, for regime 3 both are to be used. Okay. So, we will kind of solve the two cases as a part of tutorial tomorrow. They are also part of your assignment that we have put up. Okay. And thereafter we will look at the rest of the cases. So, the most general case. So, this is what, for example, your textbook does. What your textbook does is it considers regime 1, 2 and 3 together. So, regime 4 is a separate case and 1, 2 and 3 is a unified case. So, that is how people in Europe design the system. People Europe outside of UK. In India, UK and US, they did it based on the multiple regimes. Okay. All of those are equivalent. It is just that under limiting cases, if the rate of reaction is very slow, very fast and so on, under limiting cases, this most general regime will become equivalent to regime 1 or regime 2 or regime 3. Okay. All right. So, yeah, that brings me to end of this lecture, and tomorrow we will run this as a kind of a tutorial. Okay, all right, thank you.